Hello and welcome to Add-on. So today we will learn about the Miller indices and learn the process of determining them. So first off, what are Miller indices? Think of them as a unit set of numbers that help us to identify the orientation of a crystal plane in relation to the three main axes, which is the x-axis, y-axis and the z-axis. They are essentially the address of that plane within the crystal, and we sometimes call them the crystal indices. So imagine we have a plane in a crystal, and let's call the plane ABC. So we have these axis points OA, OB and OC. So each of these points represent where the plane cuts across the x-axis, y-axis and z-axis. But what exactly are we measuring when we are finding these intercepts? Well, we are measuring the distance along each axis using A, B and C. A, B and C are the unit lengths along the x-axis, y-axis and z-axis, and they are known as the lattice parameters. And lattice parameters are basically the rulers for measuring the distance within the crystal. Now let's jump into the three steps to determine the Miller indices for plane ABC. BC. Our first task is to determine where our plane ABC cuts across each axis. So from this diagram we can see that we will express these intercepts as multiples of our lattice parameters, which are A, B and C. A along x-axis, B along y-axis and C along the z-axis. So if the plane runs parallel to one of these axes, say the z-axis, what would be its intercept? Well, the intercept would be infinity, because it never crosses the axis. Now once we have our intercepts, the next step is to calculate the reciprocal of each intercept value. This means we simply flip the numbers and take the reciprocal. Say we have the intercepts as 2, 3 by 2 and 1. Then we will take the reciprocals which will be equals to 1 by 2, 2 by 3 and 1, right? And if an intercept is infinity, its reciprocal would be 0, as 1 by infinity is 0. Then our last step is to convert the reciprocals that we obtained into the smallest possible set of whole numbers, and this process ensures that we have simplest form of these indices. So for example, we have 1 by 2, 2 by 3 and 1. So we will, to convert this reciprocals into clear fractions, we will multiply them with the LCM of the denominators, and the LCM of 2 and 3 in this case is 6, so we will multiply it with 6. So after multiplying, we have the clear fractions in this case as 3, 4, 6, and this is the set of Miller indices for this particular example. And why do we even care about the Miller indices? Why is this important? Well, it's all about symmetry. The Miller indices tells us where planes sit within the crystal. Plane with the same Miller indices are parallel to each other, and if a plane is parallel to an axis, the corresponding Miller index will be 0. And if the plane cuts into the negative side of an axis, we mark that as negative. So that index will be negative in that negative region. So by knowing these indices, scientists can study and predict a crystal's properties, which is the key in material science and engineering. So let's recap what are the steps. So first of all, we need to identify the intercepts along each axis. Then we will take the reciprocals of those intercepts. And after that, the final step is to convert them to the smallest integer in order to find the Miller indices. Thank you for watching.